Hey everyone, welcome back to lecture 45. In this lecture, we're going to be continuing with the generation algorithms. So, in the part one, we covered two things, right? We covered two orderings, the Lex and the gray code, and the next permutation algorithm, right? Which is the scan, swap, and the sort. So, today, what we're going to do is we're going to take a look at two more algorithms, which is going to be the next subset and the next combination algorithm, right? Now, these two have the same pattern, which is we're just going to scan and increment and reset the tail. So, but the idea is the representations are going to be totally different, right? Subsets, we're going to make them into binary strings, and combinations will become increasing sequences, right? So, watch for symmetry in this case. It makes both algorithms almost trivial. Okay, so let's start with next subset. It's the cleanest of the three algorithms, and it will make binary counting feel brand new. Okay, let's understand next subset now. The idea is first we need a clean way to represent the subsets, right? So here's the trick. This is what we're going to do, right? Every subset of n elements corresponds uniquely to a n-bit binary string, which is basically one to one, right? And nothing is missed in this case, and there are no duplicates. So the rule is very simple. What you're going to do is you're going to label your elements 1 through n. So for example, over here, you have these numbers. What you're going to do is you label 1 through n. For each bit position I, if the bit I is 1, element is in the subset. And if it is 0, element is not in the subset. Okay, so I hope this makes sense. Let's just quickly take an example of this. Okay, so let's say we have a set with three elements. We have eight subsets in total for this one. So we have the set 1, 2, 3. You have 2 to the power of 3, which is eight subsets in total, right? Watch for the mapping. So each subset gets its own unique 3-bit binary string. So let's just consider the empty subset. MC set would be the bit string 000, right? The subset with just element 1 is going to be 100. Subset 1 3 is going to be 101. And subset 2 3 is going to be 011, right? And the full set will be 111. So 2 to the power of n subsets in total, 2 to the n binary strings in total, right? It is perfect one-to-one matching happening. So generating subsets becomes generating binary strings, right? Which is counting up in binary. And that's going to make the next subset algorithm almost trivial. So let's see the algorithm now. Okay, so the next subset algorithm, let's just walk through it, right? It has three steps, just like the next permutation that we covered. Okay, so step one is find the rightmost zero, and we start by scanning from right to left. Step two is flip that zero to a one, and the final step is zero out everything after it. Now, here's the interesting part, right? This algorithm is exactly just adding one to a binary number. So the three steps, because binary addition has three moves. So let's just consider an example, right? When you add 1 to a binary number, the rightmost bit takes the carry. So if it's a 0, it becomes 1 and it's done, right? And if it's a 1, it becomes a 0 and passes the carry left. The carry keeps moving left through any ones and flipping them to 0 until it hits a 0. And that 0 becomes a 1 and carry stops. Right? Don't worry if it didn't make sense. Let's just try to quickly understand it once again. Right? So you keep on flipping left through any ones, flipping them to 0 until it hits a 0. That 0 becomes a 1 and then carry stops. So what the algorithm is doing is it's just naming what the carry does. Right? Rightmost 0 equal the vary where the carry lands, and the ones to the right of it get rolled over. Okay, let's take a look at an example now, right? Let's run next on the bit string 11010111. So starting position, scanning right to left for the first 0. Okay, so position 8, we're going to skip it, right? We're going to skip position 7 as well. And we're going to skip position 6 as well. Okay, so finally, we're going to reach position 5, and that's where we find the first 0, right? From right to left, we are going. Okay, now that's going to be our target. Now, what we're going to do is we're going to flip this 0 to a 1. Okay, after we are flipping, we're going to zero out everything after it. So position 6, 7, 8 all became 0. And in the final, what we have is we have 1, 1, 0, 1, 1, 0, 0, 0. And in decimal, that's 215 plus 1 equal to 16. You can actually check this as well in binary calculation. Right? So it's pretty much just binary addition, and there's just you have these 3 steps for it. Okay, now let's understand the combination representation, right? Once again, we're going to start with the representation. So combinations are unordered selections, right? The idea is if you're picking 3 items, the order you pick doesn't really matter. So the set 135 is basically equal to the set 531. Okay. Now let's take a look at the sorted sequence trick, right? For an algorithm to work in the lexical order, we need a canonical form, right? So you want to sort the elements in the ascending order. The combination 135 becomes the sequence 135. So this combination is a unique ordered sequence. Now, every combination has a unique sorted sequence. So 315 becomes 135, 513 becomes 135, right? They are the same thing because the order doesn't matter. So one combination means one sequence. Now, let's take a look at an example now. Say we are choosing 3 from 6. So C of 6 choose 3 is 20 combinations, right? In Lex order, starting with 1, 2, 3, then 1, 2, 4, then 1, 2, 5, then 1, 2, 6, then 1, 3, 4, and you keep going on. So the sequence keeps growing, right? You have 15 more. So you have 1, 5, 6. At 10, you have 2, 3, 4. It keeps on going. Next one. And at the very end, you have 4, 5, 6, and that's going to be the last one. So 20 combinations in Lex order, start to finish. Now let's take a look at the algorithm for this one. It's going to be subtler than the other two. Okay, the next combination algorithm, now we have 3 steps again this time, right? But we have a new idea, which is the ceiling. So each position in a sequence has a maximum value it can take. So position I maxes out at n minus r plus I value. Right? That's going to be the ceiling of each position. Okay, so let's just consider one example, right? For n equals 6 and r equals 3, ceilings are position 1 maxes at 4, position 2 maxes at 5, and position 3 maxes at the value 6. Now, these caps leave room for later positions. Now, let's take a look at the algorithm. Okay, so it has 3 steps. Step 1, find the rightmost position not at the ceiling. Okay, step 2, bump that position up by 1. And then step 3 is you reset the tail. For the reset, positions after the bumped one get the smallest valid fills. So each becomes one more than its predecessor. Let's take a look at an example now. So let's say you have n equals 6 and you have r equals 3. Take the combination 1, 2, 3. Find the rightmost position not at the ceiling, which is position 3 is at 3. Ceiling is 6, right? So it's not capped. Okay. So I equals 3. You bump it up. So A3 becomes 4, right? Now, step 3 is vacuous, right? Because no positions after 3. So it becomes 1, 2, 4. Now, let's try next of 1, 2, 6. Okay. So for 1 to 6, position 3 has the position value 6, which is at its ceiling, right? So we skip it. Now position 2 has the value 2, and the ceiling is 5. So it's not capped. So I equals 2 in this case, right? Now bump position 2. So A2 becomes the value 3. Now step 3 is reset position 3 to 1 more than the position 2, which is going to be that A3 becomes 4. So the answer in this case is 1, 3, 4. Okay, let's take a look at one more example now, which is going to be the 3, 5, 6. So in this case, position 3 and 2 are both at ceilings, right? And position 1 is at 3, and ceiling is 4. So it's not capped. So bump 4 and reset it to 4, 5, 6. Okay, so I hope you were able to understand this example. Okay, so that wraps up the generation algorithms. We covered three algorithms. Now, they all have the same pattern, it's just that they have different objects. So, the unified pattern is very simple. You find the rightmost thing that can be incremented, right? Second step is you increment it. And the third step is you reset the tail, right? And that's the recipe for all three of them. Okay. More broadly speaking, this whole chapter was about generation, right? As opposed to counting. So counting gave us formulas and generation gave us the actual algorithms, right? I hope you understand the difference in both of them. Okay. In the next lecture, we're going to be starting with the graph theory, which is we're going to cover vertices, edges, paths, and cycles. So I'll see you guys in the next lecture and best of luck for your exam.